We measure the cosmic microwave background, the leftover radiation from the Big Bang.
But you would like something more that you could bring to people, saying that this is very valuable and tangible stuff.
Well, scientists have already made a major discovery, the Higgs boson. Some call it the God particle.
Okay, ready? Right here, on the border between France and Switzerland, is the biggest science experiment ever built.
Deep inside CERN's underground labs, something incredible has been found with the Super Proton Synchrotron. This undercover, four-dimensional force messes with the paths of zooming particles. Hidden in the depths of phase space, this unknown force, called the 4D ghost, throws the delicate dance of particles into chaos. As researchers dig into this weird thing called resonance, it's starting to shake up everything we thought we knew about particle physics. What's lurking in those hidden dimensions? Is this third dimension that we live in even real? Let's crack open the hidden calculations to see what's really going on.
The CERN particle accelerator was turned back on. So far, no new paranormal phenomenons. The experiment is making some nervous that it could create a cosmic black hole. Ariane Daytil verifies what we know about the particle experiment.
The hidden dimensions found in particle accelerators. Physicists at CERN have made an extraordinary discovery within the Super Proton Synchrotron, capturing what they describe as a 4D ghost in the machine's vast network of tunnels. This ghost is not a specter in the traditional sense, but rather an elusive, invisible structure that has the power to alter the paths of speeding particles. Researchers have painstakingly measured and detailed this structure, which exists in a complex realm known as phase space. Phase space allows scientists to visualize different states of motion, and this particular structure requires 4 such states to be fully represented, hence its description as 4-dimensional. This intriguing finding is the result of a phenomenon known as resonance, which happens when multiple systems vibrate or move in synchrony. Understanding and measuring this 4-dimensional structure marks a significant advance in the field of particle physics. It helps scientists get closer to solving a persistent challenge that affects all magnetic particle accelerators, particles straying off their intended paths. Physicist Giuliano Franchetti from the GSI in Germany explains the problem. Particles often don't follow the path we plan for them. They deviate, get lost, and this leads to what we call beam degradation. This degradation makes it tough for scientists to maintain the specific conditions they need for their experiments. Resonance, the underlying cause of this issue, is a syncing of oscillations, similar to how planets affect each other's orbits through gravity, or how a tuning fork will start to vibrate in response to the sound waves from another fork. By understanding this 4-dimensional ghost, scientists can better predict and control these deviations, paving the way for more precise and successful experiments in the world of particle physics. Particle accelerators, like the ones at CERN, use incredibly strong magnets to create electromagnetic fields. These fields are crucial because they guide and push particles along a set path at high speeds, aimed at precise targets for experiments. However, these magnets aren't perfect. Sometimes, small flaws in the magnets can cause what scientists call resonance. This resonance creates unwanted magnetic patterns that interact with the particles. These interactions can nudge the particles off their intended paths, causing issues in the experiments. Normally, the movement of particles in these machines is described in simple terms, just 2 coordinates on a flat surface, up and down or left and right. But the real situation is much more complicated. Scientists need to use 4 coordinates to accurately describe what's happening inside an accelerator. This allows them to map not just the flat 2-dimensional paths, but also additional dimensions that take into account the deeper complexities of particle movement. Mapping these 4 coordinates is a challenge because it stretches beyond our usual ways of thinking about space and movement, making it a tough concept to grasp. Physicist Giuliano Franchetti explains that to truly understand the resonance in particle accelerators, it's necessary to consider not just one plane of movement, but both horizontal and vertical directions. This approach might seem simple in theory, but changing how one normally thinks about these problems can be quite challenging. It took years of persistent work and complex computer simulations for scientists to start to understand the impact of resonance on particle beams. These efforts eventually enabled Franchetti and his colleagues, including Hans Bartok and Frank Schmidt from CERN, to use special devices called beam position monitors to detect and analyze the magnetic anomalies affecting the accelerator. By examining around 3,000 beams, they meticulously recorded whether the particles were drifting off to one side or staying centered. This careful, detailed work allowed them to create a detailed map showing where and how resonance was disturbing the accelerator. This map is a key step in solving the intricate puzzles of particle physics and ensuring the accuracy and success of future experiments. What makes our recent discovery so extraordinary, explained physicist Giuliano Franchetti, is that it provides real insight into how individual particles are influenced when they come into contact with each other in what we call coupled resonance. This resonance is a kind of syncing up that happens at a microscopic level, and seeing it in action confirms a lot of what we've previously only been able to guess at through theoretical models and computer simulations. The excitement in Franchetti's voice was palpable as he discussed the implications of their findings. He shared that the next phase of their research would involve developing a detailed theoretical framework that accurately describes how particles interact under these specific conditions. This new theory could be revolutionary, offering scientists new methods to prevent the particles from straying off their intended paths, a common issue known as beam degradation. By improving the stability and accuracy of the particle beams, the team at CERN hopes to enhance the quality of their experiments, paving the way for more precise and groundbreaking research in particle physics in the coming years. Meanwhile, popular podcast host Joe Rogan has stirred up a wave of curiosity and concern with his recent announcement about a mysterious and somewhat alarming discovery at CERN that even the experts can't quite wrap their heads around. Deep under the city of Geneva lies the Large Hadron Collider, CERN's flagship particle accelerator, usually humming along quietly as it probes the secrets of the universe. But something unusual has recently occurred, something that wasn't supposed to happen, which has puzzled the scientific community and sparked a flurry of questions. What does this unexpected event signify about the nature of our universe? And more intriguingly, could this phenomenon have any connection to the Mandela effect, where large groups of people remember events differently than how they actually happened? These questions highlight the profound and often mysterious implications of CERN's work as they continue to explore the very fabric of reality. At the heart of CERN's groundbreaking work is a mission to recreate the conditions of the universe mere moments after the Big Bang. How do they aim to achieve such a feat? Through the Large Hadron Collider, a giant machine that accelerates particles to near light speeds before smashing them together. This process creates conditions similar to those that existed just after the Big Bang, allowing scientists to study the building blocks of our universe in ways never before possible. However, something has been found out about these experiments that no one can explain. But what has been discovered, and why is the entire scientific world in shock about it? With new questions from CERN's latest discovery, let's look at how this giant of science got started and what drives it. How global scientists team up at CERN. The tale of CERN, the European Organization for Nuclear Research, and its monumental creation, the Large Hadron Collider, is a captivating exploration of scientific progress and international collaboration. Nestled on the edge of Geneva and established in 1954, CERN was born from the ashes of World War II with a noble goal: to use science to foster peace and unravel the mysteries of the universe. Initially, the organization began with 12 founding countries, but it has since grown into a global powerhouse, with numerous nations joining to contribute to its cutting-edge research. This commitment to international cooperation is fundamental to CERN's ethos, creating a unique environment where some of the world's sharpest minds from diverse backgrounds collaborate, breaking down political and geographical barriers. The construction of the Large Hadron Collider, LHC, is perhaps CERN's most ambitious project. Started in the late 20th century and completed in the early 21st, the Large Hadron Collider stands as a testament to human ingenuity and the quest for knowledge. It's the largest and most powerful particle accelerator in the world, spanning an impressive 27 kilometers in circumference and situated 100 meters underground. This giant ring, composed of superconducting magnets and advanced accelerating structures, pushes particles to speeds close to that of light, smashing them together in high-energy collisions. These collisions mimic the conditions that existed just moments after the Big Bang, providing scientists a window back in time to study the fundamental particles and forces that shaped our early universe. The operation of the Large Hadron Collider marks a significant epoch in the history of science, reflecting decades of technological innovations and advancements in fields such as superconducting magnet technology, vacuum engineering, and computational sciences. Each experiment conducted within its circular chamber could potentially unlock new discoveries about our universe, offering insights into the mysterious conditions of the early cosmos and possibly new physics beyond the current theories. The story of CERN is not just about building a machine, it's about building bridges between countries and cultures through the pursuit of a common goal. It's a story of overcoming immense technical challenges, where every cable, magnet, and bit of software must work in perfect harmony to explore the smallest scales of nature. As particles collide within the Large Hadron Collider, they tell stories of the particle's existence billions of years ago, enabling physicists to piece together the puzzle of our universe's fabric. Through this relentless pursuit of knowledge, CERN embodies the spirit of discovery and the endless human quest to understand the unknown. As we stand on the brink of potential new discoveries, each experiment at the Large Hadron Collider not only probes the boundaries of our understanding, but also tests the limits of human collaboration and innovation. The travel of CERN and the Large Hadron Collider continues to inspire and challenge us, as it steers us through the intricate dance of particles that underpin everything in our universe. The significance of creating this mini Big Bang is huge. By observing the particles produced in these high-speed collisions, scientists can uncover clues about how the universe came to be. In 2012, scientists at CERN made a groundbreaking discovery that would change our understanding of the universe. The Higgs boson, this elusive particle often referred to as the God particle, plays a crucial role in the standard model of particle physics. It's responsible for giving mass to elementary particles, the tiny building blocks that make up everything in the universe. But what does that really mean? Imagine the universe as a vast ocean, and particles are like ships sailing through it. The Higgs boson is similar to the water in the ocean, creating a kind of resistance that gives particles their mass. Without the Higgs boson, particles would zip through the universe at the speed of light, weightless and unable to form the atoms and molecules that make up stars, planets, and even life itself. The discovery of the Higgs boson was a monumental achievement for CERN and the entire scientific community. It confirmed the existence of the Higgs field, an invisible energy field present throughout the universe. This field interacts with particles, slowing them down and providing them with mass. The Higgs boson is a particle associated with this field, much like a wave is associated with the ocean. The implications of this discovery are huge. It solidifies our understanding of how the universe works at a fundamental level and opens the door to new mysteries. The discovery of the Higgs boson is a key that unlocks further mysteries of the universe as scientists continue to study this particle and its interactions. However, some recent secrets have come to light that have shocked everyone. This is where the concept of dark matter comes into play. Dark matter is one of the universe's greatest mysteries. Despite making up about 85% of the universe's mass, dark matter doesn't emit, absorb, or reflect light, making it completely invisible and detectable only through its gravitational effects on visible matter. This elusive substance plays a crucial role in the universe, influencing the structure of galaxies and the universe's overall structure. So, where does CERN come into the picture? CERN is on a quest to understand dark matter secrets through the Large Hadron Collider. Known for colliding particles at incredibly high speeds, the collider creates conditions that mimic the early universe moments after the Big Bang by analyzing the particles and forces generated. As we uncover more at CERN, we must ask, what risks come with messing with nature's deepest secrets? Taming the wild forces of particle physics. This is where the tale of Anatoly Bugorski stands as a reminder of the immense power and potential dangers associated with particle accelerators. Bugorski, a Russian physicist, experienced something almost unimaginable while working on the U-70 synchrotron at the Institute for High Energy Physics in Protvino, Russia. He accidentally exposed his head to a proton beam in 1978. The incident occurred when Bugorski was checking a malfunctioning piece of equipment. Unbeknownst to him, the safety mechanisms had failed, and as he leaned in, a proton beam shot straight through his head. Remarkably, he reported seeing a flash brighter than 1,000 suns, but felt no pain at the moment of the accident. The beam entered the back of his head and exited near his nose, leaving a path of destruction in its wake. The areas of his face and head that the beam touched swelled up, and over the next few days, the skin at the beam's entry and exit points peeled off, revealing the path the beam had burned through parts of his brain. Despite the severity of the incident, Bugorski survived. He continued to work in science, completing his PhD after the accident. However, the long-term effects were significant. He lost hearing in his left ear, where the beam had entered, and the left side of his face remained paralyzed. Over time, he experienced seizures and occasional complex partial seizures. The incident involving Anatoly Bugorski is a stark reminder of the formidable power and potential dangers of particle accelerators. These machines, designed for probing the deepest mysteries of the universe, harness immense energies and, without rigorous safety protocols, can pose serious risks. Bugorski's accident, while highly unusual and rare, serves as a crucial lesson in the necessity of strict safety measures when handling such complex scientific machinery. This accident not only underscores the raw power of these accelerators, but also raises broader concerns about what the experiments at CERN might inadvertently reveal or trigger. Delving into CERN's research, one of the most fascinating areas is the exploration of the theoretical possibility of parallel dimensions. This notion, which might seem like something from a sci-fi movie, is actually a serious subject in the field of theoretical physics. Researchers propose that our universe could be just one of numerous universes in a vast multiverse, each governed by its own unique set of physical laws. The question then arises, how might the experiments at CERN, particularly those conducted in the Large Hadron Collider, uncover these hidden dimensions? The Large Hadron Collider, a marvel of modern science, conducts high-energy particle collisions that recreate conditions similar to those just after the Big Bang. These extreme environments could potentially reveal clues about dimensions beyond our familiar three-dimensional space. Theoretical physicists speculate that if additional dimensions do exist, they might impact the behavior of particles in detectable ways. For instance, during collisions, some particles might vanish into these unseen dimensions, leaving behind distinct energy signatures that could be measured. Moreover, the phenomenon of gravity, notably weaker than other fundamental forces like electromagnetism, could be explained by its extension into these extra dimensions, suggesting why it appears diluted in our observable universe. Exploring other dimensions isn't just theoretical curiosity. It could revolutionize our understanding of the universe. The possibility that particles can interact with dimensions outside our observable realm offers exciting new avenues for physics, potentially helping to solve some of the most perplexing mysteries, such as the nature of dark matter and the fundamental forces that govern our universe. By pushing the boundaries of known physics, CERN's Large Hadron Collider might one day provide empirical evidence of these parallel dimensions, fundamentally altering our conception of reality. As we continue to explore these possibilities, the importance of maintaining stringent safety protocols becomes even more evident. The power harnessed within CERN's particle accelerators is immense, and the potential discoveries could be profound. However, the risks, as highlighted by the Bugorski incident, remind us of the need for extreme caution. Every experiment, Every collision and every test conducted in the quest to uncover these secrets must be approached with a deep commitment to safety and ethical responsibility. Thus, as we venture deeper into the unknown, the lessons learned from past accidents serve as a guide, ensuring that our pursuit of knowledge is both safe and responsible. The potential to discover parallel dimensions could fundamentally change our understanding of the universe. If multiple dimensions are confirmed, it would support string theory, which says particles are tiny strings vibrating at different frequencies. These strings could stretch into other dimensions, connecting our universe with others in the multiverse. Moreover, uncovering parallel dimensions could answer some of physics' biggest mysteries, such as the nature of dark matter and the fundamental forces that govern the universe. If dark matter interacts more strongly with forces in other dimensions, it could explain why it's so difficult to detect using conventional methods. CERN's theories of the possibility of parallel dimensions is not a speculative endeavor. It's a journey to answer serious questions about the nature of reality. While the concept of a multiverse might seem like the stuff of fantasy, the science behind it is very real, grounded in mathematical theories and high-energy experiments. As CERN continues to push the boundaries of what's possible, we might just find that our universe is part of a much larger, more complex cosmos than we ever imagined. So why are scientists terrified about what these theories of parallel dimensions have uncovered? CERN's experiments with parallel dimensions have exposed us to a concept that was once thought to be just a conspiracy theory. Have you ever sworn something happened one way, only to discover your memory doesn't match the historical record? This phenomenon, known as the Mandela effect, involves large groups of people remembering events or details differently from how they actually occurred. Named after Nelson Mandela, whom many incorrectly remember dying in prison in the 1980s, the Mandela effect has sparked curiosity and debate across the globe. As we push the limits, strange things begin to happen. Could our experiments be changing more than we think? Why do we misremember the Berenstain Bears? The Mandela effect refers to those puzzling moments when many people recall something differently than it actually occurred. A famous instance of this is the name of the children's book series, The Berenstain Bears. Surprisingly, a lot of people remember it as Berenstein with an E and firmly believe in this alternate spelling, even though all physical evidence shows otherwise. Another well-known example is from the classic movie Snow White and the Seven Dwarfs. Many recall the evil queen's famous line as "Mirror, mirror on the wall," but the actual line is "Magic mirror on the wall." These kinds of memory mismatches cause a lot of head-scratching and lead people to wonder why so many share the same incorrect memories. Theories attempting to explain the Mandela effect often venture into the realm of science fiction. Some theorists suggest that these widespread false memories might actually be traces from parallel universes, alternate dimensions where history has played out differently. In one such universe, perhaps Nelson Mandela indeed passed away in prison. The Berenstain Bears was really spelled with an E, and the iconic line from Snow White is the one many mistakenly remember. This theory posits that our collective memories from these alternate realities might bleed into our own, leading to the shared but incorrect recollections known as the Mandela effect. This hypothesis aligns with ideas from quantum physics and multiverse theories, which propose that our universe is just one of an infinite number of universes, each varying slightly from the others. These variations could explain why groups of people remember major historical events, spellings, and lines from movies differently than recorded or documented in our reality. If interactions between these parallel worlds occur, they might subtly influence our collective memory, leading to the discrepancies that fuel the Mandela effect. This blending of memories from different universes could offer a tantalizing explanation for why large groups of people hold the same false memories, suggesting that our reality might be more interconnected with other unseen universes than we previously thought. Another intriguing example of the Mandela effect involves the famous line from the movie Star Wars, The Empire Strikes Back. Many fans vividly recall Darth Vader revealing his paternity to Luke Skywalker with the phrase, "Luke, I am your father." This line has been quoted, parodied, and referenced countless times in popular culture, reinforcing the collective memory of the phrase. However, upon rewatching the film, viewers are often surprised to discover that the actual line is, "No, I am your father." While intriguing, the connection between the Mandela effect and parallel universes remains speculative and firmly within the realm of theoretical physics and science fiction. Most psychologists and neuroscientists attribute the Mandela effect to more mundane aspects of human memory, such as confabulation, suggestibility, and the way our brains encode, store, and recall information. Memory, they argue, is not a perfect record of past events, but a reconstructive process that can be influenced by a multitude of factors, leading to widespread but inaccurate recollections. But where does CERN fit into this picture? Some speculate, albeit controversially, that CERN's high-energy experiments at the Large Hadron Collider might go beyond a quest for understanding the universe's fundamental particles. They suggest that these experiments could somehow influence reality itself, causing ripples that lead to the Mandela effect. The theory says that by recreating conditions similar to those just after the Big Bang, CERN might inadvertently affect our timeline, or even create alternate realities that intersect with our own. It's essential to approach this theory with a critical mind. The collider, while powerful, operates within well-understood physical laws, and there's no scientific evidence to suggest it can alter the past or create parallel universes that merge with our own. The experiments conducted at CERN are meticulously planned and analyzed, with safety and ethical considerations at the forefront. However, one incident that happened at CERN made the scientific community worry that perhaps these safety considerations were not as strong as once thought. In 2022, during the third run of the Large Hadron Collider at CERN, an unusual event captured the attention of scientists and the public alike. A prolonged disturbance in the Earth's magnetic field was observed, an anomaly that stood out due to its duration and intensity. This incident sparked curiosity and concern. Could the high-energy experiments at the collider have influenced our planet's magnetic shield and opened a hole to a parallel universe? The Earth's magnetic field, an invisible force that protects us from solar winds and cosmic rays, is crucial for maintaining the balance of our planet's environment and the safety of electronic infrastructure. When this field is disturbed, it can lead to geomagnetic storms affecting satellite communications, GPS systems, and even the electrical grid. Every experiment at CERN could lead to amazing findings. But what if they also bring unexpected dangers? Let's find out what could go wrong. Did CERN open a portal to another dimension? The 2022 incident stood out because the disturbance in the Earth's magnetic field lasted much longer than usual fluctuations typically caused by the sun's activity. This unusual event triggered a comprehensive series of investigations to probe the nature of this disturbance and to determine if there was any direct link to the operations of the Large Hadron Collider. Scientists from a variety of disciplines, including geophysics, solar physics, and particle physics, came together to sift through and analyze the data collected during the time of the anomaly. The first step in the investigation involved a thorough examination of the collider's operational records. Teams of scientists delved into the logs to check for any out-of-the-ordinary occurrences or specific experiments that might have influenced the Earth's magnetic field. They scrutinized the energy levels and the rates of particle collisions, as well as the setup of new experiments that were being conducted during the collider's third operational run. Simultaneously, experts in solar physics examined data related to solar activity to determine whether a rare solar event, such as an unusually strong solar flare or a significant coronal mass ejection, could have been responsible for the disturbance. Understanding the solar conditions during that period was crucial because the sun's behavior is known to significantly affect the Earth's magnetic shield. In addition to solar and collider data, the investigation also considered geological factors that might influence the Earth's magnetic field. Scientists looked into whether movements within the Earth's molten core or other deep Earth processes could have contributed to the extended disturbance. By comparing current findings with historical data, the team sought to identify any past incidents with similar characteristics, which might offer clues about natural cycles or unique occurrences that could shed light on the 2022 event. This thorough, multidisciplinary investigation underlined the broader implications of such human-conducted high-energy experiments. The potential effects on Earth's natural systems raised important questions about our ongoing activities and emphasized the critical need for continuous monitoring and diligent research to protect the delicate balance of our planet's environment. As the study progresses, the connection between the collider's operations and the observed magnetic field disturbance continues to be a key focus of scientific inquiry. Despite exhaustive research and collaboration, the exact causes of the disturbance remain elusive, leaving scientists and the public with unresolved questions about what really occurred during that notable anomaly. The ongoing efforts to decode this secrecy reflect the commitment of the scientific community to understanding and mitigating the impacts of our most advanced technological endeavors on the natural world. Uncharted territory. CERN's groundbreaking experiments, particularly with the Large Hadron Collider, push the frontiers of what we know about the universe. But with this exploration comes a series of ethical and existential questions. What are the risks of diving into realms of physics that are still shrouded in secrecy? And how do we balance our quest for knowledge with the responsibility to avoid unforeseen consequences? The pursuit of understanding the fundamental particles and forces of the universe is undeniably noble. Yet, as we inch closer to replicating conditions that existed at the dawn of time, we go into uncharted territories. Theoretical physicist Sean Carroll expresses this sentiment well, emphasizing the importance of approaching these scientific endeavors with both curiosity and caution. He suggests that while the pursuit of understanding quantum mechanics and other complex phenomena is crucial, the scientific community must also be mindful of the potential implications of their discoveries. Carroll, among other experts, often discusses the need for a balanced approach to scientific discovery. The excitement of potentially uncovering new particles, forces, or even dimensions is tempered by the responsibility to consider the broader impact of these findings. For instance, the speculation around CERN's experiments potentially affecting the Earth's magnetic field or opening gates to parallel dimensions, while largely theoretical, shows the need for rigorous safety and ethical standards in scientific research. The conversation around the ethical implications of CERN's work also extends to the use of vast resources, both in terms of funding and intellectual capital. With significant investments directed towards understanding the universe, questions arise about prioritizing research that addresses immediate global challenges. However, as Carroll and others would argue, the pursuit of fundamental science often leads to unforeseen benefits that can address broader societal issues. But have previous experiments done at CERN led to benefits in our daily lives? While CERN is primarily known for its exploration of the universe at the smallest scales, its contributions extend far beyond the world of particle physics. The research conducted at this prestigious institution has led to practical applications that touch various aspects of our daily lives, particularly in medicine and technology. One of the most notable examples of CERN's broader impact is in the field of medical imaging. Techniques developed from particle detection technologies used in experiments like those at the Collider have been adapted for medical use. For instance, positron emission tomography scans, a staple in modern medical diagnostics, have benefited from advancements in particle detection technologies pioneered at CERN. These scans, which help doctors identify cancer and monitor heart and brain functions, are a direct testament to how high-energy physics research can contribute to life-saving medical technologies. Pentaquarks, exotic forms of matter consisting of 4 quarks and 1 antiquark bound together, unlike the more familiar protons and neutrons made of 3 quarks. This discovery opened new avenues in understanding the strong force that binds subatomic particles together. This helped further enrich the field of particle physics. The impact of CERN's work goes well beyond theoretical physics and the quest to understand the universe's fundamental forces and particles through practical applications in medicine and technology. CERN demonstrates the tangible benefits of investing in fundamental science. These advancements, often unexpected, highlight the broader value of curiosity-driven research, reinforcing the importance of supporting scientific endeavors that push the boundaries of human knowledge. CERN and the Large Hadron Collider stand at the crossroads of awe-inspiring discoveries and mysteries, from the groundbreaking detection of the Higgs boson to the strange nature of dark matter and the theoretical possibilities of parallel dimensions. We're continually reminded of the vastness of the unknown that lies ahead. Could these hidden dimensions at CERN uncover secrets beyond our wildest theories? What are they not telling us? Drop your thoughts below, and don't forget to like and subscribe for more revelations.